Well, welcome back, everybody. Today I'm going to be talking to you about milk protein in dairy goats. Again, my name is Dr. Gail Carpenter, and I'm the State Dairy Extension Specialist with Iowa State University. Now, we talked about this a little bit in the milk fat video, but just a little bit of review here. When we look across all mammalian species, we see quite a bit of variation in terms of different components. Milk fat, I want you to notice, varies quite a bit more than milk protein does. The two milk proteins that I have up here on the screen are casein and whey. And you can see that those do vary quite a bit across all species, but milk fat is going to vary quite a bit more. And in general, it's a lot easier, or we see a lot more in milk fat variation than we see in milk protein variation. So even within a flock of goats, we'll see that fat can vary quite a bit from individual to individual, and milk protein isn't going to vary or fluctuate quite as much. Now, like I alluded to in the last slide, there's two different main types of milk proteins. If you remember the nursery rhyme of Little Miss Muffet, she sat on a tuffet eating her curds and whey. And curds and whey are going to be our two main types of milk protein. So the curds are going to be what we make cheese from, and that's what we refer to as casein proteins. The whey proteins, which you may know from protein powders that you might consume in your smoothies, that's going to be whey proteins. And they vary a little bit, or they vary quite a bit actually, in terms of their overall structure. And they also vary in terms of what they're used for when we process this milk into cheese or other products. You can see here that there is also quite a bit in casein and whey composition. For the most part, most species are going to have higher casein than whey, and that's true for goats as well as a lot of other species. So most of the protein in goat milk is going to be casein proteins. So this is a representation about what those casein proteins actually look like. You see that we have different types of casein. So the purple circles are going to be alpha S1 casein. The light blue circles are going to be alpha S2 casein. Pink circles are going to be beta casein. And you can see that those all clump together to form this micelle, or this little ball of casein molecules. So this ball of casein molecules is called a micelle. The alpha S1, alpha S2, and beta caseins, they're all hydrophobic. They don't want to interact with water. If you think about mixing oil and water together, that oil is hydrophobic as well. So oil doesn't mix in with water if you put them together in a cup or in a bowl. Most of the parts of a casein micelle are going to be the same way. They separate from water. They don't want to mix in with the water. So an important component of that casein micelle is the kappa casein. The kappa caseins are these little hairs that stick out of the sides of the micelle here. Those are what's called amphiphilic, so they do interact with water. And because they can interact with water, that's what keeps the casein micelles suspended in a milk solution and not floating to the top like milk fat does. The cement that holds these micelles together are the calcium phosphate groups, and that's important because of what I'm going to talk about on this next slide. When we curdle milk proteins to make cheese, there's two things that we need. One of those is acid. Acid is going to lower the pH to dissolve the calcium phosphate. So that's going to release the glue that holds those micelles together. Rennet is also used in cheese making. And the reason for that is because it is an enzyme that shaves off those little casein hairs. So when rennet shaves off these little squiggly things that stick out of the casein micelle, that makes those micelles clump together. And when these micelles have clumped together, we call that curdling. And curdling is the first step of making cheese. Milk fatty acids we talked about in the milk fat slide, and I just want to come back to them here because of some of the important concepts that we talked about in the milk fat presentation. Milk fatty acids there is a strong correlation of de novo milk fatty acids to milk fat. We talked about that in the milk fat presentation. I showed you some of the graphs that show that that's true. When we increase de novo fatty acids, we do that as a result of good rumen fermentation and high VFA production. A couple ways that we can do that are by reducing stocking density, as well as optimizing feed intake in these goats. Now, the reason that I'm bringing this up again is because there is also a very strong relationship of de novo fatty acids to milk protein. So if we make a healthy rumen with lots of VFA production from those rumen microbes, that not only increases our building blocks for milk fat, but it provides more precursors for milk protein as well. And the reason for that is that there's a balance between energy and protein in the rumen. There's a symbiotic relationship between the rumen and its microbes. So microbes are going to be what's breaking down the feed in the rumen, and they release these volatile fatty acids, which, as I talked about, are the building blocks for milk fat. But when these microbes are released from the rumen as well, they flow out of the rumen and they're digested in the small intestine. As they're digested in the small intestine, they actually provide a lot of amino acids that are used for milk protein production. They are a very high quality source of protein, and they're a very digestible source of protein. We sometimes refer to microbial crude protein as MCP, which you can see there in that figure on the left side of your screen there. To maximize our microbial crude protein, we need a balance of dietary protein, dietary energy, and dietary forage. A balance means that we don't need too much of any one of these things, and you should be working with a nutritionist to make sure that all of these things are in balance with each other. But we don't want to overfeed dietary protein to get more milk protein, nor do we want to overfeed energy or forage. Keeping all of these things in balance with each other is what's going to make those microbes happy and allow them to ferment the feed that's in the rumen. So good rumen health promotes microbial crude protein synthesis. As the microbes break down this dietary forage, they're releasing the volatile fatty acids that are building blocks for milk fat. And they also need a source of nitrogen as well as a source of energy to grow. The rumen microbes are really cool because they don't need dietary nitrogen, or they don't need nitrogen in the form of crude protein. They can just take straight nitrogen. So that's one reason that we might feed urea in certain rations to ruminants, or we might feed alfalfa, which is high in nitrogen but not necessarily high in amino acids. So the microbes take that nitrogen that's not as amino acids, they convert it into a very high quality protein source. That's what makes the rumen cool. That's actually what makes ruminants one of the more sustainable species in terms of food-producing species. And it's a great way to increase microbial crude protein and milk protein in the goat's milk.